There is a quiet layer beneath everything you can see and touch. Beneath the table, beneath the chair, beneath the floor and the ground and the bedrock below. Beneath all of it, there is a realm, so small that ordinary words begin to lose their meaning. Not because the ideas are too complicated to explain, but because the things happening there are genuinely unlike anything in our everyday experience. Not unusual in the way a thunderstorm is unusual, or a deep ocean is unusual. Unusual in a way that is, after more than a century of study, still not fully resolved by the people who know it best. This is the world of quantum mechanics. And tonight, rather than rushing toward conclusions, we are going to walk through it slowly, through its history, its strange results, its competing explanations, and the open questions that have kept some of the most careful minds in science busy for generations. There is no urgency here. The ideas will arrive when they arrive. Let us begin at the beginning, not with modern theory, but with the way people used to think about matter, and why that thinking eventually gave way to something new for most of recorded history. People who thought seriously about the physical world asked a fairly natural question: what is everything made of? The ancient Greeks proposed various answers. Some suggested water, the one substance that could be found in solid, liquid, and vaporous forms. Others proposed fire or air, or a combination of several fundamental elements. One tradition, associated with the philosophers Leucippus and Democritus, proposed something quite different: that if you kept dividing any material into smaller and smaller pieces, you would eventually reach a piece that could not be divided further. They called this indivisible unit the atom, from the Greek word for uncuttable. This was a remarkable insight for its time. The idea that matter is not continuous but made of discrete, fundamental units lay mostly dormant for many centuries. It was revived and placed on a scientific footing in the early 19th century, when the English chemist John Dalton used careful measurements of how substances combine during chemical reactions to argue that each element consists of its own distinct kind of atom, and that chemical compounds are formed when atoms join in fixed ratios. Dalton's atoms were invisible, undetectable by any instrument of his day, but the mathematical patterns in his data were convincing enough that the idea gained traction by the late 19th century. The atom was widely accepted in principle, even as direct evidence, for it remained elusive. Chemists had organized the elements into a periodic table, noticing that elements with similar properties appeared at regular intervals. Physicists were studying heat, light, and electricity with growing precision. And into this landscape came the first hints that the atom itself might have internal structure, that it was not, in fact, the irreducible building block the Greeks had imagined. The discovery of the electron in 1897 by the British physicist J.J. Thomson was a turning point. Thomson was studying the behavior of electrical discharges in near vacuum tubes, the glowing beams of cathode rays that had fascinated experimenters for years. By carefully measuring how these beams bent in electric and magnetic fields, he established that they were made of particles far smaller than any atom, each carrying a negative electrical charge. These particles were later named electrons, and their existence immediately posed a puzzle. If atoms contained negatively charged electrons, what provided the balancing positive charge, and how were the two arranged? Thomson proposed one model, a diffuse sphere of positive charge with electrons embedded throughout, like raisins in a pudding. It was a tidy idea, but it was wrong. The correct answer came from a celebrated experiment in 1910 and 1911, conducted by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden in Manchester. They directed a beam of positively charged alpha particles produced by the decay of radioactive radium at a thin foil of gold, and then placed detectors all around the foil to see where the particles went. If Thomson's model were correct, the alpha particles should have passed through the diffuse positive charge of the gold atoms with barely a nudge. Most of them did, but a small fraction deflected sharply, some bouncing nearly straight back. Rutherford famously compared this to firing artillery shells at tissue, paper, and having them bounce back at you. The explanation was that almost all the mass and all the positive charge of an atom was concentrated in an incredibly small, dense central nucleus. Electrons orbited that nucleus at a distance, and the atom was mostly empty space. A gold atom was not a solid ball. It was something like a miniature solar system, with a tiny dense sun at the center and electrons far out in the surrounding void. This model was satisfying in some ways, and immediately problematic in others. Classical physics had a well-known prediction. An electrically charged particle moving in a curved path radiates energy as electromagnetic waves. If electrons were circling the nucleus, they should continuously lose energy, spiraling inward and collapsing into the nucleus within a fraction of a second. Atoms should be unstable, but atoms are plainly not unstable. They persist. The hydrogen atom that existed a billion years ago is the same hydrogen atom today. Something was wrong with the classical picture. The small-scale world was playing by different rules. The path toward those rules had already begun, somewhat separately, in the study of light. By the end of the 19th century, physics had a very successful theory of electromagnetism, developed by James Clerk Maxwell in the 1860s. Maxwell had shown that electric and magnetic fields could support traveling waves, and that visible light was one example of such waves, differing from radio waves and infrared radiation only in frequency. Light, in this picture, was a continuous wave spread through space, but there were certain experimental results that a continuous wave model could not explain. One of them was the spectrum of light emitted by heated objects. When a piece of metal is heated until it glows, it emits light across a range of frequencies, and the peak of that emission shifts toward shorter wavelengths, higher frequencies as the temperature increases. The classical theory of electromagnetic radiation predicted that at very short wavelengths, the emitted energy should increase without limit. In practice, it did not. The real spectrum had a definite peak and fell off at short wavelengths, rather than climbing to infinity. This failure of the classical theory was known as the ultraviolet catastrophe. In 1900, the German physicist Max Planck found a mathematical formula that matched the observed spectrum perfectly. But to make the formula work, he had to introduce a strange assumption that the oscillating atoms in the heated metal did not emit energy continuously but in discrete packets. The energy of each packet was proportional to the frequency of the radiation, with a constant of proportionality that became known as Planck's constant, a tiny number written with the letter H. Planck himself was not entirely comfortable with this assumption. He thought of it as a mathematical trick, a way to make the numbers work, rather than a deep statement about nature. But 5 years later, in 1905, a young patent clerk named Albert Einstein took the idea seriously and extended it in a new direction. Physicists had observed another puzzling phenomenon when ultraviolet light shines on certain metal surfaces. Electrons are ejected from the metal. This is called the photoelectric effect. The puzzling part was the pattern. One might expect that brighter light carrying more energy would eject electrons with more energy. In fact, what mattered was the frequency of the light, not its brightness. Light below a certain frequency would not eject electrons at all, no matter how bright. Light above that frequency would eject electrons, and increasing the brightness increased the number of electrons ejected but not their energy. The energy of the individual electrons depended only on frequency. Einstein proposed that light itself came in discrete packets, quanta of light, each carrying an energy proportional to frequency. These packets were later named photons. A single photon with enough energy could eject a single electron. A brighter beam just meant more photons, so more electrons were ejected. But the energy per photon, and therefore the energy per electron, stayed the same. This explained the observed pattern exactly. Einstein's proposal was significant, because it suggested that the quantization of energy was not just a quirk of how matter emits radiation. It was a property of radiation itself. Light, the paradigm of a continuous wave, came in discrete lumps. This dual nature of light, sometimes behaving like a wave, sometimes like a stream of particles, was deeply strange. Waves and particles were supposed to be distinct things. A water wave spreads through space, passes through multiple openings simultaneously, and interferes with itself. A particle is a localized object, going through one place at a time, not capable of interference. Yet light seemed to be both, depending on what you asked it to do. The resolution of this apparent contradiction would take decades and would never arrive in quite the tidy form people hoped for. What emerged instead was quantum mechanics, a mathematical framework that worked extraordinarily well, that predicted experimental results with unmatched precision. But that came with an interpretation, a story about what was actually happening that defied ordinary intuition. Let us trace the next steps. In 1913, the Danish physicist Niels Bohr proposed a new model of the atom that drew on Planck's quantization idea. Bohr suggested that electrons in an atom could only occupy certain specific orbits, each corresponding to a specific energy level. An electron could jump from one orbit to another, but it could not sit between them. When it jumped from a higher orbit to a lower one, it released energy in the form of a photon, with a frequency determined by the energy difference. When it absorbed a photon of exactly the right energy, it could jump to a higher orbit. This model explained something that had been mysterious for decades: the fact that atoms emit and absorb light only at specific frequencies, rather than across a continuous range. When hydrogen gas is excited by an electrical discharge, it glows, but not with a continuous rainbow of colors. It glows at a handful of precise frequencies, specific lines in the spectrum, always the same. Bohr's model predicted those frequencies accurately for hydrogen. It was a triumph, but Bohr's model was also a strange hybrid. It used classical physics for the orbits themselves, but imposed quantum rules on top, the rule that only certain orbits were allowed, and that electrons jumped between them by absorbing or emitting discrete quanta. There was no explanation for why those particular orbits and no others. It was a recipe that worked without being a theory that explained. The deeper explanation came in the 1920s, from several directions at once. The French physicist Louis de Broglie proposed in 1924 that if light, a wave, could behave like a particle, then perhaps matter made of particles could behave like a wave. He derived a formula relating the wavelength of a particle to its momentum. The heavier and faster the particle, the shorter its associated wavelength. For everyday objects, this wavelength is so tiny as to be completely undetectable, but for an electron, the wavelength is comparable to the size of an atom. And if electrons have wave-like properties, then the allowed orbits in an atom are precisely those in which the electron wave fits neatly around the nucleus, without destructively interfering with itself. Only certain wavelengths can form a stable standing wave around the nucleus, and those correspond exactly to Bohr's allowed orbits. De Broglie's idea was soon confirmed experimentally. When electrons are passed through narrow slits or crystal lattice, they produce diffraction and interference patterns the unmistakable signatures of waves. Not small waves, not metaphorical waves, real wave-like behavior, completely inconsistent with electrons being simple billiard ball particles. An electron passing through two narrow slits simultaneously produces an interference pattern on a screen. Behind them, the same kind of pattern you see when ripples from two stones dropped in a pond cross each other. This wave-particle duality, the fact that particles like electrons and photons show properties of both waves and particles, depending on the experimental situation, is one of the central facts of quantum mechanics. It is not a contradiction that has been resolved. It is an established fact about how matter behaves. In 1925 and 1926, two independent mathematical frameworks for quantum mechanics were developed almost simultaneously. Werner Heisenberg, working with Max Born and Pascal Jordan, developed a formulation based on matrices arrays of numbers that represented the possible values of observable quantities and how they changed over time. Erwin Schrödinger, building on de Broglie's wave idea, developed a different formulation based on a wave equation, now called the Schrödinger equation, that described how the quantum state of a system evolved. The two formulations looked quite different, but were soon shown to be mathematically equivalent. Together, they formed the core of quantum mechanics. At the heart of quantum mechanics is a mathematical object called the wave function, usually written with the Greek letter psi. The wave function encodes everything quantum mechanics can say about a system. It does not tell you where a particle is. It tells you, for each possible location, how likely the particle is to be found there if you make a measurement. The wave function is a probability amplitude, a distribution of possibilities, rather than a single definite value. This was a radical departure from classical physics. In classical mechanics, if you know the position and velocity of a particle at some moment, you can, in principle, calculate exactly where it will be at any future time. The universe is deterministic. Every event is the inevitable result of prior causes, playing out according to fixed laws. Quantum mechanics abandon this picture. Even in principle, even with perfect knowledge of the wave function, you cannot predict with certainty where an individual particle will be when you measure it. You can only calculate the probabilities. Some physicists hoped this was just a temporary gap in knowledge, that there were hidden variables, quantities we had not yet discovered, that would restore determinism underneath the probabilistic surface. Others concluded that the probabilistic nature of quantum mechanics was fundamental, not a sign of incomplete knowledge. The debate between these positions runs through the entire history of the field. There is another feature of quantum mechanics that is equally strange: superposition. When a quantum system is not being observed or interacting with anything, its wave function can describe a combination of multiple states at once. An electron can be in a superposition of having spin pointing up and spin pointing down simultaneously. A photon can be in a superposition of two different polarization states. A particle can be in a superposition of being in two different locations. None of these are just metaphors for ignorance, as if the particle has a definite property that we simply have not measured yet. The experiments confirm that the particle genuinely does not have a definite value for the property in question until it is measured. The act of measurement changes this. When you interact with a quantum system in a way that determines the value of some property, the superposition appears to collapse to a single outcome. You do not measure spin up and spin down simultaneously. You get one or the other, with probabilities given by the wave function. This transition from a spread-out superposition to a single definite outcome is called wave function collapse, and it has been the source of enormous philosophical and scientific debate for close to a century. The trouble is that the Schrödinger equation, the equation that governs how wave functions evolve, does not describe collapse. It describes smooth, continuous, deterministic evolution of the wave function over time. If the world were only governed by the Schrödinger equation, superpositions would never collapse, they would just grow larger, entangling more and more particles into ever larger superpositions. Yet measurements do seem to produce definite outcomes. Somehow, the smooth evolution of the wave function gives way to a single result when an observation takes place. Explaining this transition is what physicists call the measurement problem, and it remains one of the deepest, unresolved questions in the foundations of physics. Erwin Schrödinger illustrated the strangeness of this with a thought experiment that became one of the most famous in the history of science. In 1935, he described an imagined situation. A cat is placed inside a sealed box, along with a small quantity of a radioactive substance, a radiation detector, a flask of poison gas, and a mechanism that will shatter the flask if the detector triggers. The radioactive substance has a 50% chance of emitting a particle within a given hour. If it does, the detector fires, the flask breaks, and the cat dies. If it does not, the cat lives. At the end of the hour, before anyone opens the box, what is the state of the cat? According to a straightforward application of quantum mechanics, the radioactive atom is in a superposition of having decayed and not having decayed. The detector is in a superposition of having fired and not having fired. The flask is in a superposition of being intact and being broken. And following the chain, the cat is in a superposition of being alive and being dead. Schrödinger intended this as a reductio ad absurdum, a demonstration that quantum mechanics, applied carelessly to the macroscopic world, leads to absurd conclusions. A cat cannot be simultaneously alive and dead. The point was not that cats are literally quantum objects, but that the theory needed a clearer account of where the quantum world ends and the classical world of definite outcomes begins. The thought experiment succeeded spectacularly, not by resolving anything, but by making the problem vivid. Physicists and philosophers have been arguing about its implications ever since. The standard response in the decades following Schrödinger's thought experiment was associated with Niels Bohr and became known as the Copenhagen interpretation. Though Bohr himself was somewhat inconsistent about the details, and other physicists elaborated on the idea in various ways, the Copenhagen interpretation holds, broadly, that quantum mechanics is a tool for predicting the results of measurements. The wave function does not describe reality as it exists independently of observation. It describes what we can know about the results of measurements. When you make a measurement, you get an outcome. The wave function tells you the probabilities, asking what the wave function refers to in between measurements. What the cat is doing inside the closed box is, on this view, not a well-formed question. Physics is about what can be measured, and between measurements, there is nothing meaningful to say. This position has a certain austere elegance. It sidesteps the measurement problem by essentially refusing to ask the question, and for practical purposes, it works. Physicists working in the Copenhagen spirit have built lasers, transistors, MRI machines, and solar cells without needing a definitive answer to what the wave function really means. The formalism is enough. But for many physicists and philosophers of science, refusing to answer the question felt like giving up on the project of understanding nature. The question of what is actually happening, what the physical world is like, independent of what we choose to measure, is, arguably, the central question of science. The Copenhagen interpretation seemed to bracket it permanently, so other interpretations emerged. And they remain live options today. One of the most discussed is the many worlds interpretation, proposed by the American physicist Hugh Everett III in 19. Everett's idea was radical in its simplicity. Take the Schrödinger equation entirely seriously. Apply it without exception to everything, including observers and measuring devices, and see what follows. What follows is that measurements never cause collapse. Instead, the entire universe enters a superposition of all possible outcomes. When a physicist measures a particle's spin and gets spin up, another version of the physicist in the same universal wave function gets spin down. Both outcomes occur. Both versions of the physicist exist. The universe branches continuously at every quantum event, producing an ever-growing tree of parallel histories. In the many worlds interpretation, there is no collapse. The wave function always evolves according to the Schrödinger equation. The appearance of collapse from within any given branch is simply the fact that different branches do not interact with each other. They become, in effect, separate histories. This is a genuinely startling picture. It requires accepting the existence of an enormous, arguably infinite number of parallel universes, most of which differ from ours in countless details. Some physicists find this ontologically extravagant, an unnecessary multiplication of realities. Others argue that it is not ontologically extravagant at all. It does not add anything beyond what the equations already say. The equations predict a branching universe. Why not believe them? Everett's interpretation was initially ignored by the physics community. It was revived in the 1970s by Bryce DeWitt, who promoted it and gave it the name meant. In recent decades, it has gained significant press support among physicists who work on the foundations of quantum mechanics and quantum cosmology. The late physicist David Deutsch was an outspoken advocate, arguing that the many worlds interpretation is the only logically consistent one. A quite different approach is the pilot wave theory, developed by Louis de Broglie in the 1920s and later, independently rediscovered and elaborated by David Bohm in 1952. In this interpretation, particles always have definite positions. They are real, localized objects at every moment, but they are guided through space by a real physical wave, the wave function that spreads through space according to the Schrödinger equation and tells each particle which way to go. The wave passes through both slits in a two-slit experiment. The particle goes through one slit, but is guided by the wave into the interference pattern on the screen. Pilot wave theory restores determinism. Given the exact positions of all particles and the exact form of the wave function, everything that follows is determined. The apparent randomness of quantum mechanics comes from ignorance of the exact initial positions, not from any fundamental indeterminacy. The probabilities are epistemic, like the probabilities in a coin flip, not fundamental. What pilot wave theory requires in return is non-locality. The wave function of an entangled pair of particles is not a local object. It cannot be thought of as a separate wave for each particle. The wave exists in a high-dimensional configuration space that encompasses both particles simultaneously, and the guidance it provides to one particle can depend on what the other particle is doing, even at a great distance. This non-locality is not optional in pilot wave theory. It is essential to making the predictions come out right. Non-locality, in some form, turns out to be a feature that quantum mechanics seems to require regardless of interpretation. This was established by a profound argument developed in the 1960s by the Irish physicist John Bell. Bell was interested in the question of hidden variables, the idea that quantum mechanics might be incomplete and that a more complete theory would restore determinism and local realism. Local realism is the intuitive idea that objects have definite properties independent of observation, and that influences can only travel at the speed of light or slower, so that widely separated events cannot instantly affect each other. Bell showed, through careful mathematical reasoning, that any theory satisfying local realism makes a specific set of predictions about the correlations between measurements on separated, entangled particles. These predictions are expressed as inequalities, mathematical constraints on how strongly the measurement results can be correlated. Quantum mechanics predicts correlations that violate these constraints. Bell's inequalities, as they became known, offered a way to experimentally distinguish quantum mechanics from any locally realistic hidden variable theory. The experiments to test Bell's inequalities were conducted by Ailing Aspect and collaborators in the early 1980s, and the results were clear. Quantum mechanics was right, and Bell's inequalities were violated. The correlations between the entangled particles were stronger than any locally realistic theory could explain. To understand what this means, consider the following kind of experiment. A source produces pairs of photons that are entangled. Their polarization states are correlated but not yet determined individually. The two photons fly off in opposite directions to two detectors, which can each be set to measure polarization along various angles. When the measurements are made at both detectors, possibly with the detector settings chosen at random, after the photons have left the source, the results are correlated in a specific way. If both detectors are aligned at the same angle, the results always agree. But the pattern of agreements and disagreements across different angle settings cannot be explained by any pre-existing local property of the photons. The photons did not carry a hidden instruction set that determined how they would respond to each possible measurement. The correlations are real, but they cannot be explained without giving up either locality or realism. Experiments, testing Bell's inequalities have been refined continuously over the decades, closing various possible loopholes, practical ways the results might have appeared to violate local realism without actually doing so. In 2015 and 2017, experiments were performed that closed the two main loopholes simultaneously, producing what physicists call loophole-free Bell tests. The conclusion holds. Nature violates Bell's inequalities. Some form of non-locality or departure from realism is unavoidable. Note that this does not mean quantum mechanics allows for faster-than-light communication. The correlations between entangled particles cannot be used to send a signal, because neither experimenter can control which outcome they will get on any individual measurement. Only the statistics over many measurements reveal the correlation. Non-locality, in the quantum sense, is subtle. It is a feature of correlations, not of information transfer. Entanglement itself, the phenomenon underlying these correlations, was named by Schrödinger in the same 1935 paper that introduced the cat thought experiment. He called it Verschränkung in German, often translated as entanglement, but also carrying the sense of intertwining or interlocking. Schrödinger recognized it as the most characteristic trait of quantum mechanics, the one that most sharply distinguished it from classical physics. Two particles are entangled when the quantum state of the system cannot be separated into independent states for each particle. The wave function of the pair is not a product of a wave function for particle 1 and a wave function for particle 2. It is a single wave function for the combined system that captures correlations between the two. When you measure the state of one particle, you instantly know something definite about the state of the other, no matter how far apart they are. Einstein found this profoundly unsatisfying. In a 1935 paper, co-authored with Boris Podolsky and Nathan Rosen, the paper now known by their initials as EPPR, he argued that entanglement implied one of two things. Either quantum mechanics was incomplete and there were hidden variables that determined the outcomes in advance, or there was some kind of instantaneous action at a distance, a spooky influence crossing space without any time delay. Einstein preferred the first option. Bell's theorem, decades later, showed that neither option fits cleanly with local realism, and subsequent experiments confirmed that quantum mechanics was right, and Einstein's preferred world was not the one we live in. This episode in physics is worth slowing down on for a moment, because it illustrates something important about the scientific process. Einstein was not simply being stubborn in rejecting the implications of quantum mechanics. He had deep and carefully reasoned objections, grounded in a philosophical commitment to the idea that physics should describe reality as it is, independently of observation. The EPR paper was a serious scientific argument. It took more than 30 years until Bell's work in 1964 and the experiments that followed for the scientific community to have the tools to respond to it experimentally. And the response was not a vindication of the common sense view, but a further confirmation of quantum mechanics and its deeply non-classical character. The resolution of the debate did not tell us what quantum mechanics means. It told us what it cannot mean. It cannot mean that particles have definite hidden properties that predetermine their measurement outcomes in a locally realistic way. Beyond that, the freedom of interpretation remains. Let us step back from the philosophical debate and look at the structure of quantum mechanics itself more closely. One of its central features, beyond superposition and entanglement, is the uncertainty principle, articulated by Werner Heisenberg in 19. The Heisenberg uncertainty principle is a statement about pairs of physical quantities that are mathematically related in a specific way, congruate but as they are called. The most familiar example is position and momentum. The principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of measuring instruments. It is a fundamental feature of quantum states. A particle cannot simultaneously have a perfectly definite position and a perfectly definite momentum. The spread in position and the spread in momentum are inversely related. Connected by Planck's constant, another conjugate pair is energy and time. The more precisely the energy of a quantum state is defined, the longer lived that state must be, and conversely, states that exist for only a very short time have an inherent spread in energy. This energy-time uncertainty has visible consequences. Atoms in excited energy states do not stay in those states forever. They eventually emit a photon and drop to a lower energy level. The lifetime of the excited state is finite, and the energy-time uncertainty principle predicts that the emitted photon will not have a perfectly sharp frequency but a small spread of frequencies. This spread, called the natural line width, can be measured in spectroscopic experiments and matches the quantum mechanical prediction. The uncertainty principle also has a less obvious but important consequence. It prevents energy from being exactly zero in any bounded region of space. The lowest possible energy state of a quantum system is not zero energy but a non-zero quantity called the zero-point energy. This is why liquid helium does not freeze at atmospheric pressure even at temperatures approaching absolute zero. The zero-point motion of helium atoms is energetic enough to prevent them from locking into a solid lattice. Quantum mechanics is not just a theory of atoms. It is a theory of all matter at the deepest accessible scale, and its domain extends far below the atom into the nucleus and beyond. The protons and neutrons that make up atomic nuclei are themselves composite objects, built from smaller constituents called quarks. The binding of quarks into protons and neutrons, and the binding of protons and neutrons into nuclei, are governed by quantum mechanical laws, specifically by the theories of quantum chromodynamics and the nuclear force, the framework that describes all the known fundamental particles and 3 of the 4 known fundamental forces is called the Standard Model of Particle Physics. It was assembled through the 1960s, 70s, and into the 80s. synthesizing the experimental discoveries of particle physics with the mathematical tools of quantum field theory. Quantum field theory is a generalization of quantum mechanics that reconciles it with Einstein's special theory of relativity. In quantum mechanics, particles can be created and destroyed. A photon is emitted when an electron drops to a lower energy level. A particle and its antiparticle can appear from the vacuum and annihilate back into energy. These processes require the relativistic energy-mass relationship. Quantum field theory provides the framework for describing them. In quantum field theory, the fundamental objects are not particles, but fields, continuous entities that pervade all of space. The electron field fills the universe. The photon field fills the universe. The quark fields, the neutrino field, the Higgs field, all of them fill the universe everywhere, at every moment. Particles, in this framework, are excitations of these fields, localized bumps of energy and momentum in an otherwise calm field. This is a profound shift in perspective. Rather than thinking of the electron as a tiny ball that travels from place to place, quantum field theory invites us to think of it as a ripple in a field that extends throughout all of space. The electron you find when you make a measurement is a localized excitation of the electron field, a temporary concentration of its energy and momentum at a point. One of the striking consequences of quantum field theory is that fields can never be completely calm. The uncertainty principle, applied to fields rather than particles, implies that even in a region of space with no real particles, a perfect vacuum, the field is always fluctuating. These fluctuations are often described in terms of virtual particles, pairs of particles and antiparticles that flicker briefly into existence and then annihilate, borrowing energy from the vacuum for a time too short for the uncertainty principle to forbid it. Virtual particles are not quite like real particles. They cannot be directly detected, and calling them particles is perhaps somewhat misleading, but their effects are real and measurable. One example is the Casimir effect. Two uncharged metal plates, placed very close together in a vacuum, attract each other slightly, because the virtual particle fluctuations of the electromagnetic field are slightly suppressed in the narrow gap between them compared to the outside. This tiny force, measured experimentally in 1948 and many times since, is a direct macroscopic consequence of quantum vacuum fluctuations. Another example is the Lamb shift, a small but measurable difference between two energy levels in the hydrogen atom that classical quantum mechanics predicted should be identical. The Lamb shift arises because the electron in the hydrogen atom is constantly being jostled by fluctuations in the quantum electromagnetic field, the same virtual photon fluctuations of the vacuum. This effect was measured precisely by Willis Lamb and Robert Rutherford in 1940, and quantum field theory's prediction of it was a significant early triumph of the new framework. The precision of quantum field theory is staggering. The magnetic moment of the electron, its strength as a tiny magnet, can be calculated using quantum electrodynamics. The quantum field theory of electrons and photons to more than 10 significant figures. The experimental measurement agrees with the theoretical prediction to the same precision. This is among the most accurately tested predictions in all of science. The electron's magnetic moment has been measured to be approximately 2.0023193043 when expressed in the natural quantum units, and the theoretical calculation matches this to within the current experimental uncertainty. The Standard Model extends this framework beyond electrons and photons to include all the known quarks, leptons, and the particles that carry the weak and strong nuclear forces. It was completed in its current form in the 1970s. With the theoretical prediction and eventual experimental discovery of the W and Z bosons, the carriers of the weak force, and the gluons that carry the strong force between quarks, the final piece was the Higgs boson, predicted in 1964 by Peter Higgs and others, and discovered experimentally at the Large Hadron Collider in 2012. The Standard Model is, by every measure, one of the greatest intellectual achievements in the history of science. It describes the behavior of all known fundamental particles through 3 of the 4 fundamental forces with extraordinary precision. It has survived decades of experimental testing without a single confirmed failure, and yet it is clearly not complete. It does not include gravity. Einstein's general theory of relativity describes gravity with equal precision in its own domain, the domain of massive objects, large distances, and the structure of spacetime. But the two theories, quantum field theory and general relativity, are, in their current forms, incompatible. Attempts to formulate a quantum theory of gravity, analogous to the quantum theories of the other forces, run into severe mathematical difficulties. The straightforward generalization produces infinities that cannot be removed by the same techniques that work in the other quantum field theories. This incompatibility becomes important in situations where both quantum mechanics and gravity are significant simultaneously. In the extreme conditions of a black hole's interior, or in the very early universe, where all the matter and energy of the cosmos was compressed into an extraordinarily small volume. In those regimes, we currently have no complete theory. The Standard Model predicts what happens. General relativity predicts what happens. But when you try to combine them, the math breaks down. Physics has a gap, and the gap is in the most extreme corners of physical reality. There are candidate theories for quantum gravity, string theory, and loop quantum gravity are the most developed, but neither has produced a confirmed experimental prediction that distinguishes it from existing theories. The problem of quantum gravity remains open. The Standard Model also does not explain dark matter, the gravitationally inferred but otherwise invisible substance that appears to make up roughly 85% of all matter in the universe. Astronomical observations, from the rotation of galaxies to the bending of light around galaxy clusters to the pattern of fluctuations in the cosmic microwave background, all consistently indicate the presence of far more mass than can be accounted for by the particles in the Standard Model. Whatever dark matter is, it is not made of any particle the Standard Model predicts. It is a new kind of matter, and we do not know what kind. Similarly, the Standard Model does not explain why the universe is made of matter rather than antimatter. For each type of particle in the Standard Model, there is a corresponding antiparticle with the same mass but opposite charge. In the early universe, at very high energies, matter and antimatter were produced in equal quantities. Yet the universe we observe is overwhelmingly matter. Stars, galaxies, planets, and people are all made of matter, with essentially no natural antimatter. Something in the early universe produced a slight asymmetry between matter and antimatter, a slight excess of matter over antimatter. And after all the annihilation of matter-antimatter pairs, that tiny excess survived to become the entire observable universe. The Standard Model contains a small amount of matter-antimatter asymmetry, a property called CP violation, but not nearly enough to explain the observed universe. The full explanation is unknown. These gaps point toward physics beyond the Standard Model. What that physics might be is one of the central questions of contemporary fundamental physics. Let us return now to the interpretational questions, because they are not just philosophical decoration. They connect to some of these open questions in important ways. The measurement problem, in its most precise form, is the question of why quantum mechanics appears to require two distinct kinds of evolution: the smooth, linear, deterministic evolution described by the Schrödinger equation, and the discontinuous, probabilistic collapse of the wave function when a measurement is made. The Schrödinger equation says nothing about measurements. It is a universal equation of motion. If it applies to everything, including measuring devices and the physicists, making measurements, then collapse never actually happens. The universe just gets more and more entangled. But then what explains the definite outcomes we actually observe? One approach that has gained considerable attention in recent decades is when a quantum system interacts with a large environment, the many molecules of air around it, the photons bouncing off it, the vibrations of nearby objects, its quantum state becomes entangled with all those environmental degrees of freedom. This entanglement happens extremely rapidly for macroscopic objects. Once the system is entangled with a large environment, the different superposition components effectively stop interfering with each other. The off-diagonal terms in the system's density matrix, which represent quantum interference, decay away exponentially fast. The system becomes, to any practical measurement, indistinguishable from a system in a classical mixture of definite states. This process is called decay, and it explains why Schrödinger cat states are never actually observed at macroscopic scales. A cat is made of roughly 10 to the power of 27 atoms, each interacting constantly with its environment. The time for quantum coherence to be lost, for the different superposition branches to decohere, is extraordinarily small, far smaller than any timescale we could hope to resolve experimentally. By the time any macroscopic observation is possible, the interference between branches has already been suppressed to immeasurably small values. Decoherence is a real physical process, well confirmed experimentally. In carefully controlled laboratory experiments with small quantum systems, a few atoms or ions, or carefully isolated photons, decoherence can be slowed and its effects studied in detail. The match between theory and experiment is excellent. Decoherence gives us a quantitative account of where the quantum classical transition lies, not at the scale of individual atoms, not at the scale of cats, but somewhere in between. Depending on how strongly the system couples to its environment and how complex that environment is. But decoherence does not fully solve the measurement problem. It explains why different superposition branches do not interfere with each other. It does not explain why, within a given branch, a single definite outcome is observed rather than all of them simultaneously. The many worlds interpretation says that all outcomes are observed in different branches. The Copenhagen interpretation says the question has no answer. Decoherence, taken on its own, does not choose. What decoherence does provide is a natural account of why the classical world looks the way it does, emerging from an underlying quantum one. It tells us that the world of everyday experience, a world of definite objects with definite properties, is not in conflict with quantum mechanics. It is, in a sense, produced by quantum mechanics. The quantum correlations that encode the definite character of macroscopic objects are real features of the underlying quantum state. They are just very hard to access directly. The same Schrödinger equation that governs a single electron also governs, in principle, the entire universe. This observation is not merely poetic. There is a field of research called quantum cosmology that takes it seriously, that attempts to apply quantum mechanics to the universe as a whole, treating its wave function as the fundamental description of all of reality across all of cosmic time. In quantum cosmology, the wave function of the universe evolves according to an equation derived by John Wheeler and Bryce DeWitt in the 1960s. now known as the Wheeler-DeWitt equation. Applying quantum mechanics to the universe as a whole raises profound and not yet answered questions about what it means for the universe to have a wave function when there is no external observer to make measurements on it. There is also a line of thought connecting quantum mechanics to information. The quantum state of a system can be thought of as encoding information about possible measurement outcomes, and the evolution of the wave function can be thought of as the processing of that information. This perspective became especially prominent with the development of quantum information theory in the 1980s and 90s, which showed that quantum systems can store and process information in ways fundamentally different from, and in some respects more powerful than, classical systems. A classical bit of information is either 0 or 1. A quantum bit, or qubit, can be in a superposition of 0 and 1. When you measure it, you get 0 or 1 with probabilities given by the quantum state. But while the qubit is in superposition and not being measured, it can participate in computations that exploit the full space of superpositions. A quantum computer with enough qubits can solve certain problems, notably the factoring of large numbers into their prime factors exponentially faster than any known classical algorithm. This is not just theoretical. Quantum computers have been built with ever-increasing numbers of qubits by research groups at universities and at companies including Google, IBM, and others. The field is still in early stages. The quantum computers that exist today are noisy and error-prone, and their practical advantages over classical computers remain limited to specific problem domains. But the theoretical foundation is well established, and the experimental progress has been rapid. Quantum cryptography is another application of the informational aspects of quantum mechanics. One of its key ideas is quantum key distribution, a method by which two parties can establish a shared secret key for encrypting messages, with the security guaranteed by the laws of physics, rather than the assumed computational difficulty of a mathematical problem. The security arises from a quantum mechanical fact. Measuring a quantum system disturbs it. If an eavesdropper tries to intercept a quantum key distribution transmission by measuring the quantum states being sent, the disturbance introduced by the measurement is detectable by the legitimate parties. Quantum key distribution protocols have been implemented over fiber optic cables and even over free space via satellite, with secure communication distances of hundreds of kilometers. There is a curious fact about all these applications: lasers, transistors, nuclear power, MRI, imaging, quantum computing, quantum cryptography, which is that they all work. They work based on the mathematical formalism of quantum mechanics, which allows us to calculate probabilities and make predictions, without requiring any agreement on what the wave function really is or what happens during measurement. The Copenhagen spirit of pragmatism has served the engineering applications of quantum mechanics extremely well, but the open interpretive questions have not gone away, and they may eventually connect to physics. Some researchers argue that different interpretations of quantum mechanics are not merely philosophical preferences, but genuinely different physical theories. Even if they make the same predictions about ordinary experiments, they might differ in their predictions about exotic situations, quantum gravity, the very early universe, the inside of black holes, where the standard formalism becomes uncertain. Others argue that the interpretations are permanently empirically equivalent and the choice between them is, in principle, a matter of preference or taste. What physics can say with confidence is what quantum mechanics predicts. It can say that particles have wave-like properties. It can say that states can be It can say that certain measurements disturb the systems they measure. It can say that entangled particles exhibit correlations that cannot be explained by local hidden variables. It can calculate the energy levels of atoms, the masses of particles, the decay rates of radioactive nuclei, the magnetism of the electron, the fine structure of spectral lines. All of this is established, tested, confirmed. What physics has not resolved is the question of what the wave function is. Is it a complete description of physical reality, or does it capture our knowledge about reality without being the thing itself? Is it something that exists out there in the world, or something that exists in relation to observers? Is the universe a single evolving quantum state, branching continuously? Or is there a single definite trajectory through possibilities, guided by a real physical wave? Or is there no underlying story, just the predictions? These are not silly questions. They are among the most serious questions one can ask about the nature of physical reality, and the fact that they remain open after a century of the most precise physical theory ever developed is itself a remarkable fact about the world, or at least about our epistemic situation within it. One avenue of contemporary research is the program of reconstructing quantum mechanics, finding simple, physically intuitive axioms from which the full mathematical formalism can be derived. The hope is that if we can identify which features of quantum mechanics are truly fundamental and which are consequences of those features, we might understand more clearly what the theory is telling us about the world. Several such reconstruction programs exist, using ideas from information, theory, and the structure of measurement. They have reproduced the full formalism of quantum mechanics from various sets of axioms, including axioms about the consistency of probability assignments and the way information about measurement outcomes can be combined. These reconstructions do not definitively settle the interpretation, but they do clarify what quantum mechanics requires at the most basic level. There is also ongoing experimental work probing the boundary between quantum and classical behavior. Physicists have created quantum superpositions of increasingly large objects, not cats, but molecules containing hundreds or even thousands of atoms, carefully isolated from their environments in vacuum chambers. These experiments test the predictions of quantum mechanics at scales where classical physics might have been expected to take over, and quantum mechanics continues to win. The boundary, if there is one, is pushed ever further by each new experiment. There are speculative proposals for mechanisms that might cause genuine collapse, physical processes that occur in addition to the Schrödinger equation and that produce definite outcomes rather than One of the most developed is the proposal by Giancarlo Gherardi, Alberto Rimini, and Tullio Weber, known as the GRW theory, in which the wave function undergoes spontaneous random localization events at a very low but non-zero rate. For a single particle, this localization happens so rarely as to be undetectable, but for a macroscopic object made of very many particles, the combined effect of all the spontaneous localizations produces something that looks, for all practical purposes, like collapse on a timescale too short to observe experimentally. The GRW theory is a genuine alternative to standard quantum mechanics. Not just a different interpretation of it, it makes slightly different predictions that could, in principle, be tested by sufficiently sensitive experiments. Those experiments have not yet been performed with enough precision to rule the theory in or out. A related proposal connects objective collapse to gravity. The physicist Roger Penrose has argued that superpositions of states that differ in their gravitational fields, different mass distributions, are inherently unstable, and that gravity causes them to collapse on a timescale related to the energy difference between the superposed states. This is a speculative idea, and it awaits experimental test, but it connects two of the deepest open questions in physics: quantum gravity and the measurement problem, the study of quantum mechanics has also intersected with questions about consciousness. Though this intersection is philosophically contested, some early discussions of the measurement problem focused on the role of an observer, and some physicists, including John von Neumann and Eugene Wigner, speculated that consciousness might play a special role in wave function collapse. The argument, roughly, was that since the laws of quantum mechanics apply to everything material, including brains, you could push the measurement problem all the way back to the observer's mind, and perhaps only the fact of conscious experience could stop the infinite regress. This view is held by very few physicists today, in part because decoherence and the development of quantum field theory have provided physical accounts of macroscopic definiteness that do not require consciousness, and in part because the proposal seems to make consciousness a fundamental element of physics in a way that is very difficult to work with scientifically. But the connection between quantum mechanics and consciousness occasionally resurfaces in more modern forms. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that quantum mechanical processes in microtubules, structural elements of neurons, might be relevant to consciousness. This proposal is very speculative and is not supported by evidence for quantum effects in the warm, wet environment of the brain, but it illustrates the persistence of the question. There is a gentler point in the vicinity of these speculations, one that does not require quantum mechanics to depend on consciousness. It is simply that quantum mechanics makes the observer the act of measurement, the process of information extraction, a central concept in a way that classical physics did not. Classical physics described a world that would unfold identically whether anyone was watching or not. Quantum mechanics seems, at least in its standard mathematical formulation, to make measurement a special kind of event, whether that reflects something deep about the role of observation in nature, or whether it is an artifact of the way we have set up the theory rather than a feature of reality itself, is an open question. The history of physics contains many examples of ideas that seemed counterintuitive, even absurd, at the time of their introduction, and that later became the unexamined background of a new generation's intuitions. Newton's idea of gravity as a force acting at a distance across empty space, without any intervening medium, seemed bizarre to many of his contemporaries, including Leibniz, who could not accept that one body could influence another with nothing in between. Relativity's insistence that simultaneity was relative, that there was no fact of the matter about whether two distant events happened at the same time, struck many people as deeply wrong. Eventually, new generations of physicists simply grew up with these ideas and found them natural. Quantum mechanics may be on the same trajectory. The generation of physicists now in graduate school has grown up with quantum information theory, with quantum computing, with Bell's theorem, with decoherence. The strangeness of superposition and entanglement is, for them, a familiar starting point rather than a shocking conclusion. It is possible that a future generation will have an intuition, perhaps a very different kind of intuition from ours, within which the current puzzles simply dissolve. It is also possible that the puzzles are genuinely deep, not just artifacts of unfamiliarity, and that resolving them will require new mathematics, new experiments, or new concepts that have not yet been invented. This is the situation that quantum mechanics leaves us in. The formalism is settled and extraordinarily successful. The interpretation, the story about what it all means, remains contested, and the questions at the frontier, where quantum mechanics meets gravity, where it meets cosmology, where it meets the origin of the universe, are questions to which we do not yet have answers. What physicists do know is this: whatever the correct account of quantum mechanics turns out to be, it will not be a return to the world of classical physics. The experiments are too clear. Bell's theorem is proven. The violations of Bell's inequalities are confirmed. Interference is real. Entanglement is real. Superposition is real. The world at its deepest accessible level does not obey the common sense rules that work so well in everyday life. It operates by rules that are strange, precise, and astonishingly effective at describing what we actually find when we look. Current experiments continue to probe the quantum world at new scales and in new regimes. Gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, rely on quantum optical techniques to achieve the sensitivity needed to detect the ripples in spacetime produced by colliding black holes and neutron stars. Quantum mechanics enabling the detection of gravitational phenomena at cosmic scales. Precision atomic clocks based on quantum transitions are so accurate that they have confirmed the predictions of general relativity in tabletop experiments. Quantum sensors using entangled states can detect magnetic fields and gravitational gradients with sensitivities beyond anything achievable with classical instruments. The applications of quantum mechanics continue to expand. The Large Hadron Collider at CERN and its successor experiments continue to probe the structure of the Standard Model and search for particles and interactions beyond it. Future experiments may probe the question of whether neutrinos, the lightest known massive particles, are their own antiparticles, a property called Majorana nature. They may detect dark matter particles directly, ending decades of inference and providing the first concrete particle to extend the Standard Model. They may measure, with greater precision, the small violations of matter-to-matter symmetry in heavy quark systems, helping to understand the cosmic asymmetry between matter and antimatter. On the theoretical side, the quest for quantum gravity continues. String theory has generated a great deal of mathematical output, including insights into the connections between quantum, gravity, and ordinary quantum field theories through something called the ADS-CFT correspondence, a duality discovered by Juan Maldacena in 1997 that relates a theory of gravity in a certain curved spacetime to a non-gravitational quantum field theory on its boundary. This correspondence has been a fruitful laboratory for understanding the behavior of quantum gravity in certain simplified cases, and it has also provided new mathematical tools for studying strongly coupled quantum field theories. But it remains to be seen whether string theory describes the quantum gravity of the real world. Loop quantum gravity takes a different approach, attempting to quantize spacetime directly by applying the quantization procedures of quantum mechanics to Einstein's general relativity. In loop quantum gravity, space itself is not continuous but discrete at the smallest scales, the Planck length of roughly 1.6 times 10 to the negative 35 meters. At that scale, space has a granular structure, like a fine lattice, rather than being a smooth continuum. Time may be similarly discrete. Connecting these ideas to observational predictions that could be tested has proven challenging. But work continues. There is also research into whether the principles of quantum mechanics might need to be modified, not in the domain where they have been tested, but in new regimes. Some proposals involve small violations of the superposition principle or the linearity of the Schrödinger equation, built into a more general theory in a way that becomes detectable only at large scales or high energies. These proposals are speculative, but they are scientifically meaningful because they make predictions that differ from standard quantum mechanics, and those predictions can be searched for experimentally. The field of quantum foundations, which studies precisely the interpretive and conceptual questions we have been discussing, has matured significantly since the 1990s. It is now a legitimate subfield of physics with dedicated research groups at major universities, conferences, and journals. The questions it addresses are no longer considered merely philosophical. They are recognized as having implications for physics and for the development of new quantum technologies. It is fitting, in a way, that the theory which tells us the most precise things we know about the physical world is also the theory that leaves the deepest questions about the nature of that world most profoundly open. Quantum mechanics measures more precisely than any other theory in the history of science. And yet what it is measuring, what is really out there between measurements, remains genuinely unclear. Perhaps that is the nature of knowledge at the edge of what can be known. We push the measurements further, we tighten the predictions, we close the experimental loopholes. And the world, patient and precise, gives us exactly the answers we ask for, while withholding the ones we did not know how to ask. The atom, once thought to be the indivisible foundation of all matter, turned out to have an interior. The electron, once thought to be a simple, charged particle, turned out to have wave properties. The photon, once thought to be simply a wave, turned out to arrive in discrete packets. Each simplification gave way to something richer, stranger, and more precise. There is no strong reason to think that we have reached the end of this process. The standard model may be superseded by something deeper. The interpretation of quantum mechanics may be settled by future experiments or future theories. The connection between quantum mechanics and gravity may be understood in ways we cannot currently imagine. For now, what we have is a theory of extraordinary power and accuracy, with open questions at its foundations that have occupied brilliant minds for a century without resolution. This is not a failure of physics. It is a sign of how genuinely difficult the questions are, and how much more there may be to discover. The universe, as far as quantum mechanics can tell us, is stranger than it appears, more intricate than it appears, and in the ways that matter most, more patient than any question we have thought to ask of it. There is a property of quantum particles that has no direct analog in classical physics, and yet it turns out to be one of the most consequential features of the quantum world. It is called spin. Spin is a form of angular momentum, a quantity related to rotation. But it does not arise from the particle literally spinning around an axis the way a top spins or a planet rotates. It is an intrinsic quantum property, one that every fundamental particle carries as a permanent part of its identity, independent of any motion through space. The existence of spin was inferred before it was understood. In 1922, Otto Stern and Walther Bloch performed an experiment in Frankfurt that has become one of the iconic demonstrations of quantum mechanics. They directed a beam of silver atoms through a non-uniform magnetic field, a field that was stronger on one side than the other. Classical physics predicted that the beam would spread into a continuous band, because the silver atoms would have magnetic moments pointing in random directions, and the force on each atom would depend on how its magnetic moment aligned with the field gradient. What Stern and Gerlach observed instead was a beam split cleanly into two discrete spots on a detector screen. Not a band, not many spots, exactly two. This meant that silver atoms had a magnetic moment that could take only two values when measured along the direction of the magnetic field. Silver has one unpaired electron in its outermost shell, and this electron carries a spin of 1/2. When its spin is measured along any axis, the result is always either positive 1/2 or negative 1/2 in the natural units of quantum mechanics involving Planck's constant. There is no middle ground. This two-valuedness is the fundamental fact. Spin 1/2 is the most common spin value for the matter particles. Electrons, quarks, neutrinos, and their antiparticles all have spin 1/2. Photons have spin 1. The Higgs boson, discovered in 2012, has spin 0. These differences in spin turn out to have enormous consequences for how particles behave collectively, consequences that shape the entire structure of matter as we know it. The key distinction is between particles with half-integer spin, 1/2, 3/2, and so on, and particles with integer spin, 0, 1, 2, and so on. Particles with half-integer spin are called fermions, named after the Italian physicist Enrico Fermi. Particles with integer spin are called bosons, named after the Indian physicist Satyendra Nath Bose. The distinction matters because fermions and bosons obey fundamentally different statistical rules when you have many of them together. There is a rule called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. An electron in a hydrogen atom can have spin up or spin down, but you cannot put two spin-up electrons in the same orbital. This principle is what gives the periodic table its structure. As you add more electrons to heavier atoms, each successive electron must go into a new quantum state because all the lower states are already occupied. The arrangement of electrons in shells and subshells, which determines every chemical property of every element, is a direct consequence of the Pauli exclusion principle. Without it, all the electrons in every atom would collapse into the lowest energy state. Chemistry as we know it would not exist, and neither would the diversity of matter that makes up the physical world. For bosons, there is no exclusion principle. In fact, the opposite tendency holds. When many identical bosons are together, they preferentially pile into the same quantum state. This tendency, first understood by Bose and Einstein in the 1920s, leads to remarkable collective phenomena. When photons are produced under the right conditions, many of them occupy the same quantum state. They are coherent, perfectly in phase. This is the principle behind a laser. A laser is not just a very bright light source. It is a source of light in which all the photons are in the same quantum state, and the resulting coherence gives laser light its unique properties: narrow, directed, capable of extraordinary precision. Under the right conditions, bosons made of matter composite particles with integer spin, such as certain atoms, can also Bose-Einstein condense. When such atoms are cooled to temperatures extremely close to absolute zero, a large fraction of them suddenly drop into the same lowest quantum state. This state is called a Bose-Einstein condensate. In a Bose-Einstein condensate, the atoms lose their individual identities and behave as a single quantum object, a coherent matter wave on a macroscopic scale. Bose-Einstein condensation was predicted by Einstein in 1924 and 25. Building on Bose's work on photon statistics, the first actual Bose-Einstein condensate made from atoms was created in 1995 by Eric Cornell and Carl Wieman at the University of Colorado, using rubidium atoms cooled to less than 170 billionths of a degree above absolute zero. They shared the Nobel Prize in Physics in 2001 for this achievement. Superfluidity is a related quantum phenomenon. At temperatures near absolute zero, liquid helium-4, an isotope of helium whose nucleus contains 2 protons and 2 neutrons, undergoes a transition to a superfluid state. In this state, the liquid flows without any viscosity at all. It can flow through channels so narrow that any normal liquid would be completely blocked. It can spontaneously climb up the walls of its container, a phenomenon called the Rollin film, defying the ordinary force of gravity as it spreads across surfaces. It transfers heat with extraordinary efficiency. These properties are consequences of Bose-Einstein condensation among the helium atoms, which have integer spin and are therefore bosons. Superfluidity in helium was first observed in the late 1930s by Pyotr Kapitsa in Moscow, and independently by John Allen and Don Misner in Cambridge. Explaining it theoretically was the work of several decades, with key contributions from Fritz London, Lev Landor, and eventually John Bardeen, Leon Cooper, and John Robert Schrief, whose theory of superconductivity, a closely related phenomenon in metals, also illuminated the physics of superfluidity. Superconductivity is the quantum phenomenon in which certain materials, when cooled below a critical temperature, conduct electricity with zero resistance. No energy is lost to heat. A current set in motion in a superconducting loop will continue flowing without any applied voltage, essentially forever. This is not merely very low resistance, it is truly zero. The electrical current is a quantum coherent state of the entire material, and its persistence is protected by the same quantum mechanical laws that protect superpositional states. Superconductivity was first observed in 1911 by Heike Kamerlingh-Ons in Lydnah, when he found that Mercury's electrical resistance dropped to zero below 4.2 degrees Kelvin, 4.2 degrees above absolute zero. For decades, superconductivity was understood only in metals that needed to be cooled to within a few degrees of absolute zero. Then, in 1986, Georg Bednorz and K. Alex Muller discovered that certain ceramic materials became superconducting at much higher temperatures, around 35 degrees Kelvin. This discovery launched an intense search for materials that might be superconducting at even higher temperatures, potentially at room temperature, which would transform electrical power, transmission, and energy storage. Progress has been significant. Some materials have been found to superconduct at temperatures above 130 degrees Kelvin, still very cold by everyday standards, but achievable with liquid nitrogen, which is far cheaper and more accessible than liquid helium. A room temperature superconductor remains elusive, but experimental discoveries have continued, and the question of whether room temperature superconductivity is achievable is one of the active frontiers of materials physics. Quantum tunneling is another phenomenon that has no classical analog and that turns out to be essential to the world as it is. In classical mechanics, if a particle does not have enough energy to surmount a potential barrier, a hill, energetically speaking, it simply cannot cross it. It will bounce back. In quantum mechanics, the wave function of the particle does not go to zero at the barrier. It extends into the barrier and through to the other side. There is always some probability that the particle will be found on the far side of the barrier, even if it classically could not get there. This is quantum tunneling. Tunneling probability depends exponentially on the height and width of the barrier and on the mass of the particle. For heavy particles and tall, thick barriers, it is negligibly small. For light particles and thin barriers, it can be significant. Electrons tunnel readily in many situations. Protons and other nuclei tunnel in atomic physics and chemistry. The tunneling of protons is relevant to the rates of certain chemical reactions and to the behavior of hydrogen atoms in some molecular systems. In nuclear physics, tunneling is responsible for alpha decay, the emission of an alpha particle from a radioactive nucleus. The alpha particle is trapped inside the nucleus by the strong nuclear force, which creates a potential well from which, classically, the alpha particle could never escape. But quantum tunneling allows a small but non-zero probability of finding the alpha particle outside the nucleus. Over time, this probability accumulates, and eventually the alpha particle tunnels out. The rate of alpha decay, the half-life of a radioactive nucleus, can be calculated quantitatively from the tunneling probability, and the agreement between theory and experiment is excellent. George Gamow worked out this explanation in 19, and it was one of the early triumphs of quantum mechanics applied to the nucleus. Tunneling also plays a role in nuclear fusion, the process by which atomic nuclei combine and release energy, which powers the sun and all other stars. Two hydrogen nuclei, approaching each other in the sun's core, repel each other electrically. Both are positively charged, and positive charges repel. At the temperatures in the sun's core, the nuclei move fast, but not quite fast enough, on average, to overcome the repulsive electrical barrier and get close enough for the strong nuclear force to take over and fuse them. Quantum tunneling supplies the probability gap. Even when a proton classically does not have enough energy to surmount the electrical repulsion of another proton, there is a small probability that it tunnels through the barrier. Multiply that small probability by the enormous number of collisions happening every second in the sun's core, and you get the steady fusion rate that has powered the sun for roughly 4.5 billion years and will continue to power it for another 5 billion or so. Tunneling is also the physical basis of a device called the scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich in the early 1980s, for which they received the Nobel Prize in Physics in 1986. In a scanning tunneling microscope, an extremely sharp metal tip is brought to within a nanometer or so of a conducting surface. Electrons tunnel between the tip and the surface across the narrow vacuum gap. The tunneling current is extraordinarily sensitive to the distance. It changes by roughly an order of magnitude for every 1/10 of a nanometer change in the gap. By scanning the tip across the surface and measuring the tunneling current at each point, one can map the surface with resolution at the level of individual atoms. The scanning tunneling microscope was the first instrument capable of imaging individual atoms in real space, and it has been an indispensable tool in nanoscience and materials research ever since. Let us turn to some experiments that probe the strangest aspects of quantum mechanics in especially vivid ways. The double-slit experiment, mentioned earlier, is the foundational demonstration of quantum wave-particle duality. Its logic is worth exploring in a little more detail, because variations on it have been used to probe some of the deepest features of quantum mechanics. In the original double-slit setup, a beam of particles, electrons, photons, atoms, or even large molecules, is directed at a barrier with two narrow slits. A detector screen behind the barrier records where particles arrive. When both slits are open, the particles build up an interference pattern, alternating bright and dark bands, indicating that each particle has passed through both slits simultaneously and interfered with itself. This is wave-like behavior when a detector is placed at one of the slits to determine which slit each particle actually goes through. The interference pattern disappears. Each particle now goes through one slit or the other, and the pattern on the screen is just the sum of two bands with no interference. This is particle-like behavior, the transition from interference to no interference, triggered by the presence of a device that can in principle determine which slit the particle used, illustrates the measurement problem in its starkest form. It is not the presence of a human observer that matters, and not even the actual act of reading the detector. What matters is whether the which slit information exists anywhere in the universe, whether it has become encoded in any physical system whatsoever. If it has, the interference disappears. If it has not, the interference persists. A fascinating elaboration of this is the quantum eraser experiment. In a quantum eraser, particles are sent through a double-slit setup with a device that marks each particle with information about which slit it used. But then, after the particle has passed through the slits and before it is detected, that marking information is erased. In many such experiments, this erasure of the which path information restores the interference pattern. The erasure does not send a signal backward in time. The experimental design is careful to make sure no classical information can propagate from the eraser to the detection event. What it shows is that the interference pattern, or its absence, is determined by whether which path information is in principle recoverable at the time of detection, not by any prior event. An even more striking version is the delayed choice quantum eraser, built on an idea proposed by John Archibald Wheeler in the 1970s and realized experimentally by Yoon-Ho Kim and collaborators in 1999. In delayed choice experiments, the decision about whether to observe which path the particle took, or to erase that information, is made after the particle has already landed on the detector screen. In a certain sense, the observation in the present seems to affect the behavior of the particle in the past. Results consistent with interference appear in those cases where the which path information is erased, and results consistent with no interference appear in those cases where the information is retained, even though, at the moment of detection, neither outcome has yet been determined. This seems paradoxical, but there is no paradox in the mathematical sense. The correlations in a delayed choice experiment cannot be used to send information backward in time. They only become apparent when the results from the detection screen and the results from the eraser device are compared after the fact, which requires a classical communication channel that obeys the usual causal order. What delayed choice experiments do demonstrate very vividly is that asking questions like which path did the particle take on its way to the screen may not have well-defined answers independent of the experimental context. The particle's past, in some sense, is not fully determined until measurements are made and compared. Wheeler himself reflected on this deeply. He proposed a picture he called the participatory universe. The idea that the universe does not have a fully determined past independent of observation, but that, in some sense, observations in the present help give shape to events in the past. This is a philosophically daring idea, and Wheeler held it with awareness of its speculative character. It remains on the edge between physics and philosophy, and it is mentioned here not as established science, but as a serious reflection by one of the great physicists of the 20th century on what quantum mechanics seems to imply about the nature of reality and time. There is a more recent development in quantum measurement theory called weak measurement, introduced by Akira Heronov, David Albert, and Lev Vaidman in 1980. Standard quantum measurements disturb the system they measure. Measuring an electron's spin gives you a definite result, but leaves the spin in a definite state, destroying whatever superposition it was in. A weak measurement involves an interaction between the measuring device and the quantum system that is so gentle it provides very little information about the system in any single trial, but causes minimal disturbance. By collecting results from many weak measurements and post-selecting on those cases where a subsequent strong measurement yields a particular outcome, one can extract what are called weak values, quantities, that can fall outside the range of ordinary eigenvalues and that give information about the quantum system's properties between measurements. Weak measurement has been used to track the average trajectory of photons through a double-slit setup, producing pictures that look remarkably like the Broglie's pilot wave trajectories, smooth curves that guide the photons through one slit or the other while the interference pattern builds up on the screen. This does not prove pilot wave theory weak. Values are not ordinary hidden variable positions, but it provides a striking visualization of quantum behavior that has generated significant discussion. Symmetry is a concept of deep importance in modern quantum mechanics and quantum field theory. In everyday usage, symmetry means that something looks the same from different angles or after certain transformations. In physics, symmetry has a more precise and more powerful meaning. A theory has a symmetry if its equations remain the same under a specific transformation, and by a remarkable theorem proved by Emmy Noether in 1915. Every continuous symmetry of the laws of physics corresponds to a conserved quantity translational symmetry, the fact that the laws of physics are the same. Everywhere in space corresponds to conservation of momentum. Temporal symmetry, the fact that the laws of physics do not change over time, corresponds to conservation of energy. Rotational symmetry, the laws being the same in all directions, corresponds to conservation of angular momentum. These conservation laws, so useful in solving physics problems, are not independent postulates. They follow from the symmetries of space and time. Quantum field theory extends this idea to internal symmetries, symmetries of the mathematical structure of the field equations that are not directly tied to space and time, but to the way different fields relate to each other. The electromagnetic force arises from a local symmetry of the electron field, the requirement that the equations remain unchanged when the phase of the electrons' wave function is changed independently at each point in space and time forces the existence of a new field, the electromagnetic field, and its photon that compensates for the phase variations. The photon, in this sense, is not added to the theory by hand. It emerges as the inevitable consequence of demanding local phase symmetry. This idea that forces arise from symmetries is the organizing principle of the Standard Model. The electromagnetic force, the weak force, and the strong force all arise from local symmetry requirements. The gauge group of the Standard Model, the mathematical structure encoding all these symmetries, is compact and specific, and it determines the particle content and the interactions of the theory almost completely. The Higgs mechanism, which gives masses to the W and Z bosons and to the quarks and leptons, arises from a further elaboration of this symmetry framework, in which the Higgs field spontaneously breaks part of the symmetry in the ground state. The search for a theory beyond the Standard Model is, in large part, a search for additional symmetries. Supersymmetry is a hypothetical symmetry between bosons and fermions, between the force carriers and the matter particles, that would require every known particle to have a superpartner with a spin differing by 1/2. If supersymmetry exists, there would be a fermionic partner for every boson and a bosonic partner for every roughly doubling the particle content of the Standard Model. Supersymmetry has attractive theoretical properties. It resolves certain technical problems in the Standard Model related to the Higgs boson's mass, and it naturally provides a dark matter candidate in the form of the lightest supersymmetric partner particle, which would be stable and interact only weakly with ordinary matter. Despite extensive searching at the Large Hadron Collider, no supersymmetric particles have been found at the energies so far explored. This has not ruled out supersymmetry entirely. The predicted masses might be higher than current experiments can reach, but it has significantly constrained the parameter space of supersymmetric theories and dampened some of the earlier enthusiasm. The quantum world also extends into the cosmos in ways that may seem surprising. The large-scale structure of the universe, the distribution of galaxies into filaments, sheets, and voids, separated by vast empty regions, traces back, in part, to quantum fluctuations in the early universe. In the first tiny fraction of a second after the Big Bang, during a period of extraordinarily rapid expansion called cosmic inflation, quantum fluctuations in the density of energy were stretched to cosmic scales by the expansion. These fluctuations became the seeds of all structure, the slight overdensities that, over billions of years, collapsed under gravity to form the first galaxies and galaxy clusters. This is a remarkable connection. The quantum uncertainty principle operating in the extreme conditions of the early universe, planted the seeds of everything we see when we look at the night sky. The cosmic microwave background radiation, the afterglow of the early hot universe, now cooled to about 2.7 degrees, above absolute zero and detectable as microwave radiation filling the entire sky, carries the imprint of those primordial quantum fluctuations as tiny variations in temperature across the sky. These temperature fluctuations have been measured with great precision by satellites including WMAP and Planck, and their pattern is consistent with the predictions of inflation combined with quantum field theory. The universe we observe is, in a deep sense, a quantum structure, its shape determined by quantum randomness in its earliest moments. There is a quantity called the cosmological constant, introduced by Einstein in 1917 and later abandoned, then later still revived by astronomical observations, that is connected to the quantum vacuum energy of all the quantum fields that fill spacetime. According to quantum field theory, the vacuum, empty space with no real particles, is not empty at all, but is filled with zero-point energy from the fluctuations of all the fields. Estimating this vacuum energy using straightforward quantum field theory calculations gives a number that is vastly larger than the observed cosmological constant in some estimates, by a factor of 10 to the power of 120. This enormous discrepancy between the quantum theoretical prediction and the observed value is one of the most glaring, unsolved problems in theoretical physics. It is sometimes called the cosmological constant problem, and it stands as a reminder that even at the interface of quantum mechanics and cosmology, where some of the deepest insights have been found, enormous puzzles remain. The story of quantum mechanics is not finished. It is a century-old story with its most important chapters perhaps still to be written. The experiments are ongoing, the theoretical debates are alive, and the questions at the frontier are as sharp as they have ever been. What matter ultimately is at its deepest level, how definite outcomes emerge from a probabilistic quantum substrate, how gravity fits into the quantum framework, why the universe is the way it is and not otherwise. These are questions that quantum mechanics has sharpened without yet resolving. In the meantime, the theory does what it has always done. It describes, with extraordinary precision, what happens when we ask the universe questions through carefully designed experiments. It answers in numbers that match, in the agreement of theory and observation across an enormous range of scales and phenomena. It does not explain why the rules are the way they are. It does not paint a familiar picture of reality. What it offers instead is something rarer and, in its own way, more profound, an honest account of what the universe tells us, when we learn to ask it the right questions. And perhaps that is enough for tonight. The questions remain, and the universe keeps its patient counsel, and the mathematics runs on quietly beneath every surface and every silence, describing a world more intricate and more surprising than any we might have imagined on our own.